Today we'll be going over quadratic vertical compression and horizontal stretch. Vertical compression and horizontal stretch occur whenever our value for A or B will be less than the parent function. In this case, it has to be between 0 and 1. In our last video, we had values that were greater than the parent functions, A and B, which were 1, so any value larger would work. Now we're going to do the opposite. It's called vertical compression because our values, the farther or the larger our x value becomes for the variable input, the more compressed our function looks on a graph. And that compression vertically also looks like a horizontal stretch, as if I pull it outwards on my function graph. Going back over the actual forms in the equation, we are going to be focusing on our A and B, what is being multiplied to our variable. Now B is our horizontal change as it is affected before our x is squared. And A is our vertical change as it is affected after our x values are squared. Another thing to go over again will be our negative. Whenever we have a negative on the outside affecting it afterwards. Our parent function staying the same. When our new function, the transformation, is negative x squared, the negative happens after every value is squared, it creates the reflection. Now there's nothing limiting what we can use for an input, our x values, so we say our domain is all real numbers for x. Our range is limited for our transformation specifically. We're saying that our y values can be any value that is less than or equal to, because it goes below 0. Now moving on to the actual lesson, our values that are less than 1. We have 1/2 as our factor that is being multiplied to x squared. It is on the outside, so this would be our A variable, which means that this is going to be a vertical compression because it affects after the squared, and it is less than 1 that we're multiplying by. If you look at our table, when we plug this into the values, they are not all whole numbers. This is because we get whole numbers when our output originally was an even number. We had an odd 9, which gave us a decimal. We had an even 4, which gave us a whole number. Odd, decimal, even, whole. By definition, even. Now, just like all the other ones, to compare it to the parent function, I'll fill out the graph now. Red, our parent function, showing that there are no changes, nothing multiplied, added, or subtracted. And our new function, using a few more points than what was given on the table, we can see that it is outside of our parent function. This is where it gives that look of being vertically compressed. My values do not increase as fast as, or my output values do not increase as fast as my parent function. Now, there is nothing changing of our vertex, our lowest point, and we're under the same situation where x can be any value. So our domain, our x values, are still all real numbers. And my range is going to be the same as the parent function. I can have any y value that is greater than or equal to its lowest point, the vertex, 0. Now, when you actually plot this on the graph, I suggest just using the whole values when you do so. As you can tell here, I used the -2 x value, a -4, a -6, and respectively on the other side, just to keep it a little bit cleaner so we're not dealing with the decimals. Speaking of which, on this problem, the reason why we have decimals is because we are multiplying by 1/2 again, but this time it is inside the parentheses. This would be a horizontal transformation. This would be our b value. Looking at the parent function yet again, staying the same, nothing changing. Same output for the same given input. Our transformation looks similar to our last transformation, if I can draw it correctly. Let's see here. If I can draw this correctly. There we go. That's about the best it's going to get. But yet again, we have it looking like it is outside of the parent function. But this time, our description is going to be a little bit different. We are affecting it horizontally. So I don't want to say it is a vertical compression like we did on the first example. Even though it looks the same, we are making a horizontal change. So I need to describe that horizontally. This would be a horizontal stretch. Looking at our x and y values, it looks like we are getting wider than our parent function. Domain, yet again, still does the same thing. We can use any x value and have some form of output. And our range will be any y value that is greater than or equal to our lowest point in this situation, which is 0. Now, when graphing these, you still need to follow the rules that are given. Our y value for a vertex is easy to find. It is whatever is added or subtracted to the end. So notice that our vertex down here is at a value of -2 for y. And same for the other one with a value of -2. The vertex are not the same based off of what's inside the parentheses. Now, if there is no horizontal compression or stretch, such as the one on the right, all we need to do is set it to equal 0, and it gives us one step. We subtract 1 from both sides, which actually states that our x value is going to be -1. And if we look at our vertex here, it lands on -1 for the x value, and we use the -2 for our y value. We can't do it as simple as that on the other problem because it has a horizontal compression. So when I set this to equal 0, I still have an extra step afterwards. I would add 1 to both sides. Give me 1/3 x equals 1. And then I get rid of the 1/3 by multiplying by its reciprocal. In this case, multiplying both sides by 3, I am given x equals 3. So instead of looking at a possible x value of 1 like we did over here with the one step, we actually get an x value of 3, which matches up with what I have. My lowest point is at an x value of 3 and a y value of -2, matching up with the end. general idea of what the graph looks like going through the vertex. I can do the same thing on the other one. Now, actually using the descriptions, we have to be careful on what they say. Our first one is fine. It has a vertical compression or stretch. So we can write it with the values that are all shown. Vertical compress is an A value. So it says vertically compressed by a factor of 1/5. And translate is our key word for the next part, giving us 9 units to the right. This being our C. It's a horizontal change, and it's adding and subtracting. And 2 units down. This is a vertical change, so it has to be A or D, and is dealing with a translation. This is adding or subtracting to the end of the equation. So our original function, our equation, oops, make sure I write everything on there. We can fill out our equation, replacing all the values that we know. We keep the y equals. We have an A value that is 1/5. We did not have a horizontal compression or stretch, so we do not need to write the B. Still leaving the x. That is a part of our function. Our C says opposite of what we have, where normally we would have a +9. We need to write the opposite, which gives us -9. Finish it out squared. And then we also have our D variable, which says 2 units down. Since it's a positive D, we write it exactly as it states, down being negative. Now our next one is the main thing that I wanted to focus on. It does have the key phrase of reflect over the x-axis. It has horizontal compression or horizontal stretch by a factor of 2/3. This would be our B. And translate up 8 units. Our reflection to fill out means that it's going to be a negative value on the outside. So rewriting the original equation again. This time when we fill everything out, we have to be careful on that inside, because right now it says horizontally stretch by a factor of 2/3. This would just be multiplying our x variable by 2/3. So writing each step down, we have y equals. The reflect across the x-axis means that it's negative. Our b variable being 2/3. We still have the x for the function. There is no c in the equation, so I can close that off. And then it says it translates up 8 units. Now, if ever you have a horizontal stretch or compression and a horizontal shift, you need to make sure that it ends up equaling out at the very end. If you were to say have the same setup of B, which is 2/3, and you had a shift of say to the right one, you need to see how it looks when it's set up to equal 0. That's the main portion there, because it's not always going to be exact same numbers as 2/3 as it will in our final equation to make sure that the vertex is where it's supposed to be.